Okay. Okay, so yeah, okay, I will start now. So this sharing is supposed to be a very casual one, and then I'll just start with talking about some of the very basic things about number theory, and then how it's useful in RSA, and then yeah, so I'll also be recapping a lot of things that you might have learned before. Yeah, so let's get started now. Okay, so the first thing is this. Let's look at set notations. So set notation is very important in everything that involve maths. So this is the very basic thing that I'll talk about. First, set is basically just a collection of things. So you can think of it just usually is described using this curly bracket, and then inside the curly bracket you just put whatever you want, right? And then it is usually described as a box. So for example, you can have this kind of box, and then this box is like you have some elements inside, and then set is just a box, and the elements inside is the 1, 2, 3, and so on. So this notation, we call this notation roster notation, or you can call it like enumerate notation. I believe there's something called like that. Basically, you are trying to list out all the things inside the set, and then in a set you can have whatever stuff that you want. For example, you can put some names. So there isn't really much restriction on what a set can be and what a set can, what elements can be put inside a set. But there are some paradox, but that is out of our scope of discussion. So we have this basic set notation, but you realize that okay. So you realize that this way of describing things is sometimes very troublesome. Like for example, you can have like if you do ... right? Let's say for example, this set does not contain the element 6. Then maybe you have to do something like until 4, and then 5, and then 6, you ignore it, and then you put 7, and then ... something like that. So you just remove the 6th element out from here. So this is not a very efficient way to describe a set. So there's also another way of describing set, which is called the which is a better notation in some sense. Also depends on many circumstances. So now we look at how to describe a set. So the usual way that you do this is that you put, like for example, I put an X here, and then I put a slash in between, and then I write X is an integer. So this basically means this is equivalent to just like 1, 2, 3, and then and so on. You also, I also need to include the negative numbers. So I just put it here: -1, -2, -3. This is basically just that. But then it is easier for us to describe a lot of things because we are using words. And then the word, this straight line here is basically such that. So you can read this set as what? This is a set of X of all the elements such that everything inside is an integer. A set of element X such that it is an integer. So it's a very easy way to describe stuff. And then, so now let's look at some of the common sets that we have, that we often encounter. The first thing is the integer set. So integer set we denote by Z, and then usually we put one line here to indicate that this is a special set. So Z is basically an integer. So like I described just now, it is basically all integer sets. And then maybe I should use the roster notation here. So this is negative infinity, and then -2, -1, 0, 1, 2, and then all the way to infinity. So this is the integer set. There's also another set that is also quite common, but not often that people will use it. It's the natural set of natural number. So this one, the set of natural number is described as n. It is all the integers starting from 1. So the natural number is 1, 2, 3, and so on until infinity. Yeah. So these two sets are one of the sort of the more common sets that we usually see. Another one is Q. I should write that this is the set of natural numbers. And then this is integers. Okay, so what is Q? Q is rational numbers. So for rational numbers, we cannot really describe it that well in roster notation. But if we use the description way to do it, we can use you can write it as something like this: P divided by Q, and where P is inside the set and Q is inside the set of C. Yep. Yeah. So here, allow me to also introduce this thing. So this means in. So it means that P is an element of Z. So if you type it in some mathematical library like or some usual way like LaTeX, then people usually use then the notation is /in. So it literally includes means that this element is in the set. So yeah, so this is the set of all rational numbers. And then I think these three are sufficient for our usage. Okay, so now I will introduce the set notations, the set operations. Firstly is the include operation that I mentioned just now. So when I say A, in set S, I use this notation. Basically means that A is an element of S. So yeah, this is one thing. So another thing is another common notation that is usually used is this notation. So when we talk about this means that this is a subset of that. Okay, let me write this as A, a big A, and then S. So this means that A is a subset of S. What is a subset? So a subset is basically that all elements in A are inside S. So subset means all elements. Okay, maybe I should write this in a better way. A is a subset of S, means that all elements of A is in S. So yeah, another some kind of you can also think of it in terms of Venn diagram. So one way to look at it is that if you imagine a set as this, so this is the space and then this is the S. So you have a lot of different elements here. and so on. So if this is a set, then A is basically inside this set. So all elements of A is in S. So this what do we mean by subset is this. And then there's also the difference between A is a subset of S versus A is subset equal of S. So the notation, the difference in here is the introduction of this line. And this line means that A could be equal to S. So there's a possibility that A is equals to S. And then if you write it like that, this will mean that that there's A is strictly smaller than S. So by strictly smaller, it means that there exists an element in here S such that it is not inside A. So means that this one is S, this one is A. So there is one element here that is not inside A. So it cannot be equal. And then, of course, you can also use it in another direction. So this is basically the same meaning as this, but I think intuitively, usually it's better to write it this way because it's more common for people to understand this. But you can also write it the other way. So this is very similar to how inequality works. Okay, so so far, I think that's basically sums up what I want to talk about sets. Oh yeah, there are also two more things. So one thing is on intersection. So this is the intersection operation, and this is the union operation. So for intersection, when I say A intersect with B, means that I only have all the elements such that X is in A and X is in B. And then union means I join both of them together. So X is in A or X is in B. Yeah. Okay, so far, any questions? That sums up all the things that I want to talk about sets. Okay. Okay, nice, great. Okay, then now I will talk about a new thing. Actually, not also it's probably not very new, but this is on devices and prime. So devices and prime, first I need to introduce this notation called the divide notation. So when I say so okay, let's just consider that we are all working in the integer. So let's say A and B is an integer. Okay, so remember this notation. When I say A, okay, so this divide is this straight line here. So what this basically means is that A divides B. So this means that A divides sorry, this one is quite bad. So what does A divides B means? If A divides B means that there exists a integer k such that AK is equals to B. It's just a very fancy notation to describe divisibility, but it's quite useful. And then we will use it quite a lot. Okay, so some things that we should know about, some properties about this divides notation. Firstly, if A divides B and B divides C, this will implies that A divides C. So the proof is pretty simple. If you can write AK is equals to B, I'll just quickly write out the proof here. So if I can write A divides B, implies that A case is equals to B for some integer K. I just put K1 here. And then B divides by C implies that BK2 is equals to C. So this will combine these two together. It means that AK1, K2 is equals to C. So this will also implies that A divides. Okay, so this is very obvious. Okay, and then the next thing is that yeah, so now let's talk about prime. So what's the definition of prime? A prime is basically so a prime, there are a lot of ways to define a prime, okay, but the most common way that people will try to define it is a prime can only be written if you want to write prime as a product of two numbers, then one of it must be 1. So a prime number is when, okay, maybe I write it like that. A number is called prime. Okay, an integer is called prime. If x, if I write x in AB, then A must be equals to 1 or B must be equals to 1. So that's the definition of prime. Sorry, any questions? Okay, never mind. Okay, so yeah, so that's the definition of prime. And then you can also define it in another way, such that if A, okay, wait, sorry, this one I should write as P. Okay, yeah, I write as P is better. So you can also define in another way, so that if P divides AB, then P divides A or P divides P. Okay, you can illustrate this with an example. Like for example, if P is like 5, and then this one is 15, then maybe I just write this as 3 times 5. Then it's very obvious that P or 5 will divide 5, right? So this first part we call irreducibility. The second part we call prime. And in integer is very nice because these two things always hold, and then you can prove one way from another. But then for some certain things, there is a situation where you could be irreducible, but you are not a prime. So that happens in some structures of mathematics. But usually for prime, this is the case. Okay, so now I want to talk about GCD. And then Euclidean algorithm. Yes. So GCD here means greatest common divisor. So what does greatest common divisor means? It basically means that so let's say if I write GCD of A and B, my intention is to find the greatest K such that K divides A and K divides B. So this is the definition of GCD. And then, yeah, so I also want to introduce another thing that I missed out just now. Okay, so this is a theorem called fundamental theorem of arithmetics. So fundamental theorem of arithmetics looks very fancy, but basically it says that every integer can be decomposed in a product of primes. For example, 10, you can write it as 2 multiplied by 5, product of primes. And then 100, you can write it as 2 times 2 to the power of 2 times 5 to the power of 5, 5 to the power of 2. So yeah, basically that you can decompose number into product of primes. So how do we find the greatest common divisor? An easy way to do it is you try and divide all the primes, all the possible primes. So like for example, let's say if I have I don't know, something like 100. I want to find the greatest common divisor of 100 and 64. So how do I do it? I can decompose 100 into 2 to the power of 2 multiplied by 5 to the power of 2. And then I decompose 64 as 2 to the power of 5, no, 6. Then for each of the prime number, I take the highest power. So here the highest power is 2, 2 to the power of 2. So the GCD of this is 4, which is 2 to the power of 2. So that's one way to do it. You can decompose all numbers into product of primes, primes power. But then this is not always easy to do, because what if this number is very large and this number is very large? Then you have to factor the number into primes, and it's not always easy to do it. For example, if you are looking at like 1, 2, 3, okay lah, just imagine a very large number. Okay, so something like that. Okay, and then you want to decompose it in product of primes. So this is hard and it is not easy to do. You have to do integer factoring, and integer factoring is hard. So how do we find GCD of two numbers quickly without factoring is the question that I'm trying to solve here. So in ancient times, Euclid introduced Euclidean algorithm. So Euclidean algorithm, what Euclidean algorithm does is that find GCD of two numbers A and B very fast. But okay, this very fast is in terms of computational power that you need to use, but basically you can do it very easily. So how does it work? First, we need to prove a property. So first thing you need to prove is that given two numbers A and B, GCD of A and B is equals to GCD of A and A plus B. It's also equals to GCD of A and A minus B. It's also equals to GCD of A minus B and B. It's also equals to GCD of A minus 3B and then B. Yeah, basically, you take two numbers, you add them, or you however you add them, or however you take the difference between them, the GCD always stays the same. So we can illustrate this with an example. Let's say if I want to look at 23, not 23, 24 and 30. So the GCD of 24, by this, if the above here is true, then we have that this is also equals to 24 and 30 minus 24, which is 24 and 6. And then you can repeat it again. You minus this part with this. So what do you get? You get 0 if you if you do something like that. 4 times 6. And then GCD of 0 with anything will become the original number. So this is equal to 6. So why do we even have? Okay, so how does this property come, and how can we prove this is the case? This is true. So yeah. Any thoughts? Or do you want to try proving it yourself? Okay, so the idea is this. First, you let the GCD of A and B equals to K. Then by the definition of GCD, we have that K is K divides A and K divides B. So this implies that K multiplied with some C1 is equals to A. K multiplied by some C2 is equals to B. So now let's look at A plus B. What is A plus B? A plus B is equals to KC1 plus KC2. So this would be K multiplied by C1 plus C2. And the nice thing about this is that K divides A plus B. Okay. So, but we are not done yet. Okay. What we prove now is we prove that GCD of A plus B and A is at least K. Because we are not sure whether, okay, if K divides A plus B, right? We're not sure if this is the largest common factor between them already. We only know that it is not the smallest. We only know that it is at least as large as k because of this. So now we need to prove that it is indeed k and not larger than k. But how do we prove it? So do you guys understand the problem of this? That it is only from this that it is only at least as large as k, but it's not equal to k. Right. So what we are trying to so the question here, right, we are trying to prove is that we want to prove that GCD of C1 and plus C2 and A is equals to 1. Because when this happens, then only we have GCD of A plus B and A is equals to K. So this is quite important. So the way that we can prove this is we assume that it is not 1. Okay, so so now our question is we want to prove GCD of C1, C2, and A is equals to 1. So we start by assuming GCD of C1 and C2 and A is not equal to 1. We know that the greatest common divisor must be larger than must be larger than 0. So if it's not equal to 1, means that it is some number k, that k is larger than 1. Okay, so this means that k divides C1 plus C2 and k divides A. Okay, and then okay, let me check something. Yeah, okay. So now we can write, we can rewrite this part, okay? We rewrite C1 as A divides, oh no, I can't rewrite that. Wait, let me confirm my proof. I shouldn't use the same K here. Just put H. And then okay, let me think for a while. I suddenly got stuck. Okay. I think I shall try something. So I write H is H divides C1. We have that C1 is equals to K, A divided by K. So this can be written as A divides by K, and then A divides by K2. No, sorry. A divides by K and A divides by K, and B divides by K. And then these two things are basically integers. So rewrite it as H and then K, A plus B. And then wait So I recall the way that to prove it is that you need to exploit the fact that K is the greatest common divisor. So if you can okay, I think this part is Okay, never mind. I think I will look back at this and then maybe I will fill up this gap um, in the next session. But yeah, basically, what happens is that we should have this property. So no matter how you take the difference or you add with each other, the GCD will always be the same. So this enables the Euclidean algorithm. So for Euclidean algorithm, basically, if you want to find GCD of A and B, oops, what do I do is that I reduce it to GCD of A, and then, oh, this thing is so annoying. And then A modulo B. So I assume here that A is larger than B. Larger than B. So then what happens is that, what is A modulo B? So A modulo B means that you take you can write A in terms of KB plus A, this one, modulo B. And then what we want is that this K is the greatest integer my pen, such that this part is positive. So basically is the remainder. So because we are taking remainder, we are taking modulo with each other. So we can repeat this process after we get GCD of A and A modulo B. I let this to become GCD of A and R. Then we repeat this process with GCD of A modulo R and R, and so on. So just keep reducing each other until one of them becomes 0 or one of them becomes 1. So by doing that, then we can find GCD very easily. And the reason that modulo works is because modulo is essentially just, so if you want to calculate so this part, right, A modulo B is just A minus KB. It is, you are just adding a multiple of a number to itself. So by what we are supposed to prove just now, this will maintain the same GCD. So maybe illustrate it with an example. GCD of 320 and 210 maybe. So you do this by taking the difference. So you do modulo, but modulo here is basically just the difference. So this one will be 110. And then 100, and this will be 10. 100, this will be 10 and 0. So the GCD of these two is 10. Okay. Yeah. Okay, so that's the Euclidean algorithm. And it is very important because it enables a lot of things in crypto. So yeah. Okay. So I think I managed to finish this part. And then, but okay, originally I also want to talk about, okay, maybe I just talk about Berserk's lemma now. So this is just a result. So Berserk's lemma says that if the GCD of A and B is equals to X, for example, then you can find K and H such that this thing holds. K and H are integers. And the way that this is proven is by using Euclidean's algorithm. So notice that what happens here is that you are just like in the what you get in the end here is just some integer combinations of the original two numbers. And then you can push it backwards, which we call the extended Euclidean algorithm. To prove this Bernoulli's lemma. So, for example, if GCD of 3 and 5, we know is 1, then we can write 3 plus something. So we need to find K and H here. But what is the K and what is the H here? We can eyeball this. The K here is -2, and the H here is 2. So perhaps another example, 7 and 10. So GCD of 7 and 10 is 1. Then we can write, we want to find K and H such that this is 1. Then I can let K to be 3 and H become -2. This will also becomes 1. Okay. So so the proof for this thing and the proof of the Euclidean algorithm, I will postpone it to the next session. And I think that is all for today. Okay. Then so any questions? Okay, maybe let me attempt the proof again. So okay, you are saying that we have Yep. So I want to prove that yeah, like what you say in the chat. I want to prove that this thing is still equals to this, right? So for this we have that this is equals to k and then c1 plus c2 a, and we know that yeah. So I want to prove that c1 and c2 the GCD of c1 and c2 and a is equals to 1. Mhm. Yes. Okay. So yeah, let's think about this proof and then uh next session we will show the we'll prove this more rigorously. Okay. So if there are no other questions, then we can end this now.
Okay. Let me stop the